Hello, community. Today we're gonna integrate here graph machine learning as the main reasoning engine to an LLM. So what we use, an LLM, is more or less our English-speaking, very nice formulating generative AI model. But the intelligence now shifts from an LLM to a reasoning graph structure. And if you remember my tree of sorts video, now tree of sorts was with an LLM in a two-dimensional space. And now we take this tree of sorts and we put it in an n-dimensional space. We cannot do this in an LLM, but we can do it in a graph machine learning. So let's start here. We have our LLMs that we love, that we use every day. And now you use here also the possibility to access external enterprise documents. You know how to vectorize your documents. You know how to vectorize your vector database entries to find the specific content you can then provide for in-context learning to your ChatGPT or GPT-4. But what happens if you increase the information density? If you go professional? So let's say you have a network and you say, hey, analyze my social media contacts and find the people with friends that have similar interests to me, to my sport, to my activities, to my age, to my wealth group, to my whatever. So suddenly, as you see, you do not have anymore this generative AI, these autoregressive systems that just predict the next word in the chain with a probability function that it learned on the pre-training data. No. Now we go from a one-dimensional string, we go in higher dimensional graph structures. And now we can store information effectively. And you know what? In mathematics, we have graph theory for close to 100 years. So we have a powerful mathematical apparatus. Node edges in higher dimensional graph structures. So to each node, to each little dot, to each vertex, we can have now a feature tensor attached to them. And this feature tensor has all the information. And if it's a person, it is the age, it is the color of the eyes, it is the size of the nose, it is the number of friends, whatever characterize, for example, a particular person or a particular object is in the feature tensor. And then those persons, for example, on Twitter are connected. Hey, I've read this article, I follow you, I liked your article. Those are the edges. And on these edges that are mathematical abstractions, we can attach edge tensors to. Now, those are beautiful mathematical objects that we can have now. At first, we can program them, but they carry information. So you have an n-dimensional space here where we have n-dimensional feature tensors, n-dimensional edge tensors attached, and everything is interconnected in an n-dimensional vector space that is maybe normed and has a distance. So you might say, hey, yes, graph neural networks, they are great. Because you know why? Because they have a feature that makes them unique. So let's have a look at this. If we use currently our LLMs and you have an interconnect to an external vector database, a vector store, whatever you have, you just generate the next word in an autoregressive LLM like in GPT-4. So you can say, Twitter has a network structure with millions of, then you're looking for the word. Millions of users, millions of interactions, millions of whatever. Now, let's say we want to find out about this. Perform a complex network analysis of Twitter users in the region of Europe on the topic of the latest scientific news about CERN that have 10 years experience in high-energy physics and have published at least 3 physical letters B publications in the last 2 years with other authors from CERN or from Berkeley. Now, if you are a very experienced SQL user and Postgres and whatever you have, you say, hey, if I have the database, I think I can make here a query to find out exactly about this. And I would smile and say, yes, but now predict the future co-authorship and predict the future topics they will publish on. And this you cannot do in a database. For this, you need an AI system where the AI system learns the inherent pattern in the data structure, in the network analysis of Twitter, for example. Here we need an AI to extract patterns, repeatable patterns, and apply similar patterns whenever the AI system detects them. So you see clearly the borderline that happens. All of these sentences here in black doc, no problem. Postgres, database. You can do combined SQL. You get it. But the moment you say predict the future, given that there is a hidden pattern within the data, find this, extrapolate this pattern, apply the pattern, and show me the similarities, you need a graph neural network. You need graph machine learning. And the good thing is graph machine learning is here for years. It was more or less just put away on the side, pushed to the side. But you know, now we use it as a reasoning engine that inputs here reasoning data to our LLMs. We will use message parsing, attention mechanism. There are so many things that are similar, but are even more beautiful. So, again, SQL, no problem. But if you want to predict the future, if you want to have an in-depth analysis of repeating patterns in the behavior or in objects, well, we need graph neural networks. They find the hidden patterns, they can tell us something about the future, and the beauty is there's also a knowledge graph reasoning functionality they have. So if you have a complex network, the reasoning becomes now elegant and not just a tree of sorts in 2 dimension that is stumbling to perform on an LLM. Because now we have an n-dimensional interconnectiveness of the data. So here we go. This is the simple outline of the talk. We have our LLM. This is our elegant chatting interface with us. And for the reasoning to predict future patterns and the reasoning that is embedded within the graph representation, we will use graph machine learning or GML. Let's do this. Now, you need to know a little bit about graph machine learning, but the good thing is there's a video about it. Embed, for example, the graph structure in a normalized vector space. Equip it with a metric, closeness, distance emerges. There's a video to learn this. If you're interested in the representational learning aspect itself, how to encode graph structure, there's a video for this. If you go to knowledge graph embeddings, or if you're interested in the mathematics of the graph isomorphism problem and the Weisfeiler-Lehmann test, there's a video. And if you're finally interested in how to prepare the graph dataset, and you have here the training dataset, the test dataset, the validation graph dataset, how you code this in PyG or in DGL, there's a video for this. Now you might say, when I apply now this graph machine learning, for example, for the task of a link prediction in a complex network like the Twitter network, how do I code this? Well, I have a video for you. And you say, no, I'm not looking now for a node classification task in a graph convolutional network. Well, you're in luck. And even if you combine it with an SBERT system that gives you really the complexity that maybe you would need in the second week, now you guessed it. You're not satisfied? You want to go beyond the mathematics of graph neural network? You guessed it. I have a video about new topological structures emerging, what we call simplicial complexes, and how you can use them on the classical graph neural network. So you see, the topic is there. And now the task is, hey, why don't we challenge ourselves a little bit? And you know what? There's something beautiful. Because Stanford published here a new methodology where they say, let's enable in-context learning over graphs. And you might say, what is this? Well, this is the beauty. Imagine, normally with our LLMs, we have a pre-training phase, costs about $1 million. Then we have the fine-tuning phase, if you go full resolution, about $10,000, $100,000. And then, if you're a user, like GPT-4, you have no access to the fine-tuning and neither the pre-training. So you go with in-context learning in the prompt engineering, in the prompt design. So this is normally the way you can learn an autoregressive system. But now today we want to increase it a little bit. We say, okay, so somebody is doing the pre-training for us. Let's say it's Google or Microsoft spending 10 million. Why should we do this? Now, if we want to fine-tune the system on a specific task, we would have to pay for the fine-tuning. And you might say, hey, is there, in addition to the complexity to combine the graph machine learning here, now with this approach, can we get rid of fine-tuning and construct the system in a way that I have the full power of in-context learning, that I just have to be clever about the pre-training I do to the system so I can save my money here and do not perform a fine-tuning, but jump from pre-training to in-context learning and have the optimal performance. And this is what we're going to look at. We start very easy. You have different people, you have a social network. Whatever you like to choose, they are communicating constantly in different combination. Maybe he knows her or she knows him or whatever. Whatever are the relation in this network, whatever you post, whatever you watch, whatever you communicate with, whatever you interlink with, it is a graph. It is a two-dimensional graph. It is a 500-dimensional graph. It is an n-dimensional graph. From the mathematical point of view, the n-dimensional solution is there. So we just applied. Now, for you to imagine this, because we are humans, sometimes it helps if you can visualize this. You might think, hey, this is the network that looks like. No, these are the dots, and then we have the edges connecting this. No, it is more like this. You have about several 100 million dots and several more than 100 million edges. So this is the mathematical object we're interested in. So let's start here with this beautiful publication. And this is that explains everything. There's always one graph you can find in a scientific publication where you say, okay, if I understand exactly what is depicted here, I get the methodology. So let's start. What is the task? We want to have an edge classification. This is a graph machine learning task. And I want to have the edge classification task not as a fine-tuning task, but as an ICL task, as a prompt engineering task. So the goal is simple: to predict the label with the properties, or if you know now, the tensor, the edge tensor of edges in a graph. So what information is encoded in an edge? What is the property of this particular edge, given that we have a Twitter network? Or take your Facebook friends, or whatever network you like. It just has to be complex and dimensional and have several 100 million entities. So whatever is the relation is now encoded in our graph structure, graph G. And then we have here, as I told you, some examples and queries. And these examples and queries you also find now here in this visualization. Now, before we jump into it, just that you see here, we have 4 elements that we're going to talk about. The graph itself, then the prompt examples and the queries, they go together here. And then we construct here data graphs and we construct task graphs. This is important. We have a data graph and a task graph. The task graph, of course, is specific to the task that we want to achieve. we want to achieve edge classification. And since we want this in ICL, they called it a prompt graph. So the prompt graph consists of two graphs, of a data graph and a task graph. And now I will show you what we can do exactly with those two graphs. We start at the very beginning. Now, our graph G, as I showed you, is now a citation network in the scientific literature. The nodes, the dots, present the scientific papers, and the edges, the connection between them, represents the citation between papers. So each edge has a direction going from the citing paper, what we call a head node, to a cited paper tail node. So what is the easiest example? Here we have now the prompt example. So we have a head node, this is the scientific paper A. And this is in the area of computer science. And we have a tail node B, this is from the area of physics. And the edge label, if you want, is computer science. So the edge from paper A to paper B represents a citation. So what does it mean? It's simple. Paper A cites paper B. That's it. And the label, computer science, indicates here our label. Remember, we have here two nodes. And the label indicates that the research field of the citing paper, and this is paper A. And this is here our prompt examples. It shows the model now an example of a computer science paper citing a physics paper. So we already have one part. I told you there's also the query part. This is what we query our AI system with. So in this system, we have the query. The paper C is the head node and the paper D is now the tail node. And what is our goal? As I told you, we want to have an edge classification. So we want to predict the research field of paper C, the citing paper, based on its citation of the paper D. So what we are looking for is here the research field of the paper C. Model used the prompt examples to learn about the citation behavior in different research fields, and it uses this knowledge to predict the research field of new papers. Remember this? When we put new papers into the dataset and we want to find their interconnectiveness, where they belong to, we have a training dataset of 1 million examples that are similar. Now you know where we're heading for. So beautiful. So our source graph, you know, this is our G, is the original graph structure data, our citation network, all of Arxiv, all of the scientific publications on this planet. It forms the basis for the task graph. This is the task graph, using now the Prodigy framework. It is called here the source graph because it's the source, it is the basic graph, where we look always, this is our main system, our main point of reference. It is the source of the data and the structure that the model learns from. So, beautiful. Next part. The data graph now here is a subgraph of the source graph that is relevant for a particular graph. For example, what the paper mentions for each data point from both the prompt examples and the queries. Here we have our prompt examples. Here we have the first position is now the head. Second position is the tail of the node. And we have for the edge a label classification. Here it is orange and blue. Make it round and squared or whatever you like. This is just an abstract examples to show you, hey, here we have a label orange and a label blue. So we have two labels that are available for our edges. And we have a query where we say, hey, we have now a new node that we bring into the system. And you see here blue. You see this is here our blue one, the round one, and here a blue is the triangle. So we say, if we know the relations from all of them surrounding them, and for example, here in this subgraph, the blue part now, we want to know their edges. Is it orange or is it blue? Where does they belong to? This is a typical edge classification task. So what we do now, so easy. Again, for each data point from both the prompt examples, so all our data point here and the queries, we take also here these new data points. We first construct its data graph by retrieving the context from the source graph. So we are looking now, for example, here on the first example, we have here in green, round, and triangle. So we are looking now here, we go back here to our main graph and we look here at the subgraph that contains those elements. And as you can see here, this is exactly the subgraph that lives here. So we take this, or you can call it an epsilon environment, you can call it a one jump environment or a two hop, or whatever you choose a particular complexity of a subgraph. So we extract the subgraph from the source graph that is relevant to that data point. This subgraph is the data graph. Yes. Now we do this for each and every here of our data points in the prompt examples and in our queries with the new element. And you see in the data graph, we get now for our points of interest, all those and those, we get their connectivity, their connectome pattern, their graph substructure. And we need this for the embedding that will happen later on. So we know how those are integrated into the graph. Prompt examples, query, prompt examples, query. Beautiful. Example, in the social networks now, which serves as the source graph, this is now Twitter. If you're looking at a particular user, the data point, the data graph might include that user. This is, for example, our triangle, the friends, those are the three friends, and the connections between them. This data graph provides the local context around the data point in the source graph. So you see, you want to find here the local environment, the friends, the location, the places they go to, their interests, their hobbies, whatever. This is a data graph. Now you get it? What we do now? Now we're going to look at the task graph. Why we need a task graph? We need a task graph because we want to have an in-context learning that is focused on one specific task where we provide some examples in the prompt structure. So we have a specific task that we want that the system performs. So we have to give it information about the task. Once the data graph here is constructed for a data point, it is then extended to form the task graph, G task, by adding label nodes and edges between data nodes and label nodes as per the task requirements. So you say, okay, so what is happening now? Easy. You just take here everything we have, all the subgraph, and we have here now a data node. This is our data node, and this data node contains here all the information about the local environment of a particular data point. So our data node, V of X, for each data point, so we do this for all our subgraphs, we have now 1, 2, 3, 4, 5, and 5 is the unknown one, data nodes. And then, as I told you, our task is edge classification. And here in our examples, we have two labels, the orange label and the blue label. If we want to find out the new data points, they belong to the orange label or the blue label. So we have two classes, two choices, the orange label or the blue label. This is it. And now we just do a little trick. We connect now from each data node an edge to the label node. And we do this for all combinatorial multiples. So I know now here that this data node here has a connection that is true to an orange label node. So here I have now this connection from my data node to my label node. And this is true, so I write here a little t for true. But for the system to learn the complete manifold, I connect now my data node to the other label nodes that I know that are not correct. So I have here the connection. Now there's only two possibilities. So I just have here an edge now to the blue label node. And I know this is not the case. So I put false. So you see we have now an edge, and this edge has now some information. It has a characteristic true or false. So in our edge tensor, we have our first entry if you want. Now what we did here for the first point, we do now for all of the points, also for the points that we just added to our data set. And we want to have the information, the prediction by the AI system, what's gonna happen. Is it the blue one belonging here to the label node orange or the label node blue? This is all there is. It is as simple as this. So now something beautiful is gonna happen. This is just what I explained to you in words. You can read it here in detail. I tried to give my best. So now comes the interesting part. Till now we were talking about abstract graphs. We had no mathematical space defined for them. We have no metric on this space. We cannot talk about closeness of graphs because it's just a dot and an edge and another vertex. This is it. So let's bring this now to a mathematical space that we can make mathematical operations in and we can calculate in. In this new space, in this process that's happening now, you know it, this is a vector embedding. So we take all of the complexity of a graph and we bring it over in a vector space where each vertex becomes now vectorized. Now, if you have seen all the videos that I just showed you about graph machine learning, graph theory, you know, for the graph neural network, for the layers, we have more or less three options. We have the convolutional, the attentional, yes, this is the, like in the self-attention, the attention, and the message passing. Each three options have different strengths. Just to remind you, the attentional graph neural network is a good middle ground if you go about capacity and scaling behavior, but we want to go for the reasoning. What is the best reasoning element here? And this is message passing. Beautiful. So let's use message passing. Now we have two graphs. We have the data graph and we have the task graph. You remember our two graph structures. And now we transform both of them into a new vector space because we want both graph structures that we can compute on them, that we can apply mathematical operations on them, that we can finally do the prediction. So we have now the message passing over the data graph. Remember, the data graph captures the inherent structure and the relationship in the data. All the data points have a structure and a relationship. Social network represent the connection between users. Your, I don't know, Facebook friends. So now if we apply the message passing over the data graph, allows now the GNN to learn from this connection. So each node in the data graph sends its current embedding to its neighbors. And this is why we need the local environment of all data points. And each node updates its own embedding by aggregating the embeddings received from its neighbors. So everyone is sending information to every other node that it has an edge to. This process allows the information to be shared. This is where the complexity communicates within itself and propagates across the graph data. This is why we need the structure of the data, helping to the GNN, or the GNN performs now if you want. It learns the embeddings and the specific embeddings that are characteristic for this specific graph. So it captures the structure of the data. And the data is organized in a graph. Beautiful. Now we do exactly the same over the task graph. The task graph is an extension of the data graph that incorporates now information about the task at hand because we want to perform a task in our ICL. It includes now, as I showed you, the data node. The data node have now the details from the data graph and our label nodes that are specific to the task that we want to perform. If you think about the label nodes, as outcomes of the data point. This is the result that you want. You have either an orange label node or a blue label node. Think about this as the outcome, the result of it. As I showed you, we add edges between all data nodes and label nodes based on the task. Message parsing is now then performed over the task graphs, allowed to learn those connections between now the data node and the label node for the graph-specific task. Each node in the task graph sends the embeddings to its neighbor, exactly like here, and each node updates its own embedding, and I will show you an example because it sounds complicated and it is in an n-dimensional tensor field, so it is a little bit complicated, but I show you a very easy example. You immediately understand it. Again, we learn here the embedding, the vector embeddings in a vector space with an inner product, with a normed space where we have then a distance. Captures the data and the task information. And now you know why we have this task graph and the task information, because this will enable our in-context learning on the graph structure. So, summarize, message passing over the data graph helps the GNN to learn the structure of the data, while the message passing over the task graph helps the GNN to learn from both the data and the task. Both types of message passing are crucial to learn an effective embedding of all the nodes, which can then be used for the prediction. And you might say, hey, wait a minute, is not this the same like in the vector database, in the two-dimensional case? Where we have, from when we vectorize a document or a sentence, suddenly we have a vector of the sentence, and all the similar sentence clustered together in a vector space? Yes. Now we just go to n dimensions, have here a new level of interconnectedness given by the edges and the edge information and the edge tensors and the feature tensors. So we have a little bit more of a tensor operation here, but in principle, it is just the n-dimensional extension with additional information of a simpler case. So beautiful. We have here graph data message passing, task graph message passing, and now here the vector embeddings. Now, after we performed all the message passing processes on the data graph and the task graph, what do we have now? Now, the system has now a set of new embedding vectors for the data points. The system has optimized itself, given all the tensor information in a vector space. So these embeddings, this vector in a vector space, now capture not only the original features of the data point, the feature tensor, and the structure, the interconnectiveness, the multiple edges of the data graph, but also the relationship between the data points and the labels in the task. You remember, our task is edge classification, and we have two labels. We have the orange label and the blue label. As easy as this. And then when we construct our vectors, we get now, and then we look at the vector space. We have now clusters. We have thematic clusters here now in our newly constructed vector space that has an inner product. So the labels now are related to similar data points, will have similar embeddings. This means they will be in a similar region in our vector space that forms a cluster. What goes together is together, or is embedded together, you remember. So, will be close to each other in the new vector embedding space. Beautiful. This cluster configuration can now be used to make a prediction for new data points. Imagine we have now a query and we say, hey, I have here a new data point in my graph. But I do not know if the edge classification task, if it's an orange label or if it's a blue label. Is it a friend or is it an enemy? Is it a positive comment or is it a negative comment? Whatever classification task you have, you say, hey, I have now a new data point. But this new data point has a similarity to other points already in the network. And for the existing network, for our training data set, we know which edge characteristics we have if those points that have similar characteristic we know the result. So now here, discovering this new inherent pattern in the data, we can now predict the label of this new data point. And this is all there is to it. I told you I give here the simplest example I can think of. Yeah, it is just a vector. This is a one-dimensional something. Okay, we have a social network. Each node is a user. Easiest. Each edge represents a friendship between two users. If you have an edge, they are your friend. If you have not an edge, they are not your friend. Maybe they will become your friend. Under what circumstances will they become your friend? Do you have similar interests? Do you know this? So, we are using a graph neural network with graph machine learning to predict each user's interest based on their friend's interest. So, I have then now a new person, a new user in my social network. And I want to know what are the interests of this new user if I know his friends and what they are interested in. I can integrate this in my network. So, for example, what is interest? A list of interests, and we have a binary vector. We have just 3 interests: music, sport, technology. It's a man. The world of man is simple. Wow, 3. I mean, normally it would be just 2 items, but we have 3 items. Yeah? So, an intelligent man. Beautiful. A user that is now interested in music and technology. How would this vector, in the simplest case and oversimplification, look like? Now, music, 1. Sports, 0. Technology, 1. This is exactly the vector. 1, 0, 1. Beautiful. Vector passing, message passing process. We have some initial embedding. Somehow the system has to start. There has to be an idea how we configure the very first step, the 0 approximation. Now, the initial embedding for this user A is based on the feature tensors, on the features that the user has. The binary vector representation of the interest, it is 1, 0, 1. We just found out this. Now, when the GNN processes now the graph and the whole machinery starts to operate, it uses the feature tensors to generate the initial embeddings of the node. Somewhere it has to start. And then comes the message generation. What is a message? What is the content of a message? How do we generate a message? So, user A generates a message based on their current embedding. Now, in the simplest case, and this is not always, this is just in our example, the message could be the same as the embedding of the user. 101. Beautiful. We start with this. And then we have this message. So we send this message to all available network partners that we have an edge to. So user A sends this message to all of their friends, of his friends, her friends in the network. You can go a 1-hop, 2-hop, or 3-hop environment, whatever you choose. But at the same time, everybody is sending their embeddings. Everybody in the network, all nodes are sending their special interest, their initial embeddings. And one might have 1, 1, 1, one might have 0, 0, 1, and whatever. So everybody is sending to everybody. So now we have to aggregate the message. We want to know, how does my environment look like? What is my region of friends? What is their common denominator? So user A receives all the messages from all their friends. Let's say user A has only 2 friends. Wow, 100% more than I have. Friend B with a message 0, 1, 1. Meaning music, no. Sports, yes. Technology, yes. And friend C with a message 1, 1, 0. Now, there are a lot of methods how you can aggregate this. You can go with the sum, you can go with the max, you can go with the min, and 100 other possibilities. We go with aggregation by summation. Works also with tensors, no problem at all. So what we do? We add the messages. 0, 1, 1 plus 1, 1, 0 is 1, 1, 2. Simple as that. Great. So now we have from our environment, from all our friends, the information, but now we know what we like. So we update, we add now our internal embedding, what we like. Embedding update. User A then updates their embedding based on the aggregated messages. Simple route, again, to add the aggregated message to my user A embeddings. So you remember, user A has the embeddings 1, 0, 1. It's in blue, 1, 0, 1. And all my friends have 1, 1, 2 together. In red, 1, 1, 2. We have decided the message aggregation algorithms is a sum, so we end up with this. So you see now, in the easiest case, if you say, so of this group of people, what is their dominant interest, for example? And you see here 3 entries for technology. Then you have 2 entries for music, and the least entries, 1 entry for sports. So this is a way you get information, not only about the structure, but also about the data content of your subgraph, of your network, when we have a social network and you look at your friends. So after the message passing process is over, the updated embeddings for user R captures both their own interest, the interest of user A, and the interest of their friends in their subgraph. This embedding can then be used to make prediction about users A interests. Since the third element of the embedding is the highest, yes, most likely everybody's interested in technology. So, as simple as this, an oversimplification, don't read too much into it. I just want to show you it is not complicated in principle. The vector operation and the tensor operation, if you see the code, you might say, my goodness, what is happening here? No problem. Now you know. Beautiful. So once the embedding for each data point is available and the task-specific labels are computed, now we have a beautiful mathematical vector space where we have the notion of closeness now encoded in the vector structure. So we can use simple operation. For example, we use the cosine similarity of a measure of similarity between 2 non-zero vectors of an inner product space, our vector space, that measures the cosine of the angle between them. Yes. And if you have now the cosine similarity, you have one winner. So this you assign the label to, the label with the highest cosine similarity to the data point that is brought in new is typically considered the most likely label for that data point. So we have now decided our label is now the orange label. So this new data point has now an orange edge classification. This is because the higher cosine similarity means that the data points embedding and the label embedding that we want to predict are closer, or the closest in the embedding space, indicating that they are the most similar objects in this particular region of our constructed vector space with an inner product. Beautiful. So when we did all of this, let's reflect what we did. We have a process now that can be used to make predictions for new incoming data points, given that we have all the information of our pre-training data set of our Twitter network or our citation network or whatever. So whenever a new data point comes in and we do not know the edge classification, is this nice? Is it a friend or an enemy? You can compute the cosine similarity of its vector embedding in the embeddings of all the labels and assign the label with the highest cosine similarity to it. So we can compute here, given a specific pattern in our data structure, what is the highest probability for this. This approach allows the model to make prediction based on the learned relationship between data points and labels as captured by their vector embeddings. It is flexible, powerful, adapt to new tasks and data without the need for retraining or parameter tuning. Beautiful. Here we are again at the core. We do not want to have a retraining or a parameter fine-tuning task. So let's look at this in detail. we're missing still out one major block of methodology, and this is the pre-training. How we do the pre-training if we do not want to invest in the fine-tuning of the network. How clever we have to be to choose a specific pre-training data set. Is it going to be an instruction-based data set? Is it going to be another data set? And you're not going to believe it. For the pre-training of our graph neural network, we have now in-context pre-training objectives. This might sound as a contradiction because you say, hey, pre-training, fine-tuning, in context, suddenly we have pre-training in context. Yes, just read the pre-training objectives. We have now pre-training objectives. The authors propose a set of in-context pre-training objectives to pre-train the graph model using a large pre-training graph that is independent of the downstream graph. Yes, of course, the goal is to pre-train the model. Yes, we know. But to solve now the task in context with the same set of weights, this means without fine-tuning them. So, in my words, I would say, we have now a task description we want to have in our ICL prompt. To be successful with an ICL prompt, with an in-context training, we have to structure our pre-training method and our pre-training dataset so similar to the ICL that the pre-training is happening on a so similar body of data graphs that the system has no problem to apply ICL to it, even it has not been fine-tuned on a specific task. Makes sense. So, the pre-training task generation. The authors have two methods that they combine and a third complication, so let's look at a method. The methods are proposed to generate pre-training tasks from the pre-training data, from the pre-training graph structure, in the form of few-shot prompts. Why? Because later on, in our ICL, we have few-shot prompts. And now, these methods they have is neighbor matching and multitask. So you might say, hey, multitask. I know multitask here when I think about FLAN T5. It was fine-tuned on multitask, instruction-based. Yes, more or less. This is here. Neighbor matching, you're not going to believe this, constructs self-supervised in-context pre-training task with the goal of classifying which local neighborhood a node belongs to. I will show you in a second a visualization. You will understand it immediately. So we have two methods. We combine these methods. And we even learned here now from BERT and SBERT and contrastive learning of our AI system, of our language model, that it always helps to have a contrastive learning to accelerate the learning process. So we have here 1 plus 2 plus 3. After obtaining the few-shot prompts and label, yes, 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 the neighbor matching and the multitask, the authors construct a prompt graph and they add an additional step to augment the data. And this is simply to corrupt the data graph such that the pre-trained model learns representation that are invariant to various corruption. This is exactly what we did, for example, when we did the fine-tuning and the pre-training of SBERT. So here we go. You remember we said we want to have the pre-training dataset and the pre-training procedure in a way that this pre-training is so similar to our in-context learning in our prompt design, where we provide some examples and some query, that we do not have to fine-tune the system on the task that we want to be performed here. So therefore, given that we know what we're gonna ask the system, and we want to have no fine-tuning, this pre-training has to be self-similar to our in-context learning. So define this as a design principle here for Prodigy. Oh yeah, by the way, it's called Prodigy, Enabling In-Context Learning over Graphs by Professor also Jure Leskovich, you know him, is that we formulate each pre-training objectives in an in-context learning way. Self-similarity here, since we have no fine-tuning. Okay. This is more or less the same what I just told you. You can read it in detail, take your time. What I wanted you know, the pre-training phase allows the model to learn a general purpose representation of the graph structure data, our citation network, our friendship network, while the in-context learning phase allows the model to adapt to new tasks based that we give a small number of examples with our ICL prompt. This is all there is. Okay. I told you neighbor matching. I explained neighbor matching in a visualization for you. Here we are. Our query data point is here our yellow round data point. And we have this data point here. Now, this in black, you see here our graph structure beautifully. And now, neighbor matching pre-training task generation. The key idea is to classify whether a node or an edge, we go here with a node, is in the local neighborhood of a set of sampled nodes. So, for example, we say here a 2-hop neighbor. So we say here, you remember, we have here our labels, our orange label and our blue label. Where are they in the graph? Here we have our orange label. Here we have our blue label. And we now say, hey, are both labels in a 2-hop distance? Let's check it out. So go from the yellow round node here. We go here, 1-hop, 2-hop, and we are on the orange label. Other one, blue. What is the shortest way? We go 1-hop, we go 2-hop, we go 3-hop, we go 4-hop, we go 5-hop. So blue is not in. Blue is 5 hops away. Orange is 2 hops away. So you see now to answer the query, what is the probability that in this embedding it belongs to the orange label? You just go, for example, with how many hops is it away. Great. Now you know neighbor. The design principle is to formulate each pre-training objective in the in-context learning way. Now you know why, because we have no fine-tuning, so they must be self-similar. Yeah, otherwise, in the old way, most previous graph pre-training only pre-trained on a shared graph encoder, like our BERT model to perform various graphs with some task-specific head. I showed you when I pre-trained SBERT, we introduced task-specific head. So they require fine-tuning for another task-specific head. Over each downstream task, we don't want fine-tuning, so we make this self-similar. Beautiful. Explicitly construct in-context pre-training task in prompt graph form and pre-trains the model to solve diverse tasks in context with the same set of weights. No pre-training, no fine-tuning, such that it can perform then the in-context ICL learning directly with some examples given in our prompt. Beautiful. This was the end of pre-training, and now we have it. This is it. This, ladies and gentlemen, this is now it. This is here our visualization that we have. And now you know everything. Because now we are in the final phase. We are now here in the in-context learning for query prompts. Again, we have our graph. This is our network of friendship, of citations, whatever you want, the Twitter network. Then we have some prompt examples given and a query. So we learn from the examples given in the ICL, and we have a query in the ICL. We construct the data graphs given the local environments of the points we are given, of the data points we are given in the prompt examples. We find that local graph environment, beautiful, we embed them. Plus, we have a specific task that we are giving those examples on, and we have a query. And we want that the system learns from those examples and a complete graph and tells us, hey, given those examples, for your query, the answer is orange or blue. So we construct the task graph where we have here 2 node categories And I told you, you connect all the different options. You know this. Beautiful. This is it. And then you apply the message passing on the data graph, on the task graph. You get the embeddings of all the nodes. You calculate the causal similarity, and you're able to predict here for the queries here, is it orange or is it blue? This is all there is. Here you have the wording. This is the final thing. So, beautiful publication, Arxiv preprint. Here is it for you to read it. So, as the number of prompt examples, here are prompt examples, as they increase the auto-found, the margin of our proposed models over the baseline increases. So, the more examples you provide, the better the model will predict. Of course, if you learn a new task with just 2 examples, you are unsure about giving a new task. But if you learn a task giving 10 examples and you get a new data point in, based on the 10 examples, you know much better where it belongs to. This supports the hypothesis that the model can more effectively learn the unknown task by reasoning over the common characteristic of our prompt examples. So the reasoning that is behind this structure can now be deducted the more examples you provide to the system in ICL. Great. In general, this Prodigy model surpasses the performance of other baseline models with in-context learnings. It even surpasses the performance of models that employ fine-tuning. And in both major graph tasks, node and edge classification. So this system is really something special if you apply it, and it surpasses the other methodologies and the other models. So, great new way to have here, without fine-tuning, the node and edge classification task with the highest performance. Wow, we did it! Yes, we did it! My goodness! Yes, it was beautiful. So you see, basically a simple idea, but if you combine it, if you integrate the knowledge that you have, for example, from the mathematical of graph theory here, and you just build your graphs, why not? You combine them, you have your message passing operation that has been tested for years over graph. You use, again, simply vector embedding, simply similarity functions. You are able to have prediction about something the system has never seen before. This is the power of graph neural networks. And if you combine graph neural networks now with large language model, my God, the reasoning perspective really goes strong. I say thank you for watching. Thank you for listening. I hope to see you in my next one.